I think most people will agree with me when I say that working with numbers is a lot easier than working with just variables. So let's work through, like, I'm going to call this a type 1 where you just shoot something off. Let's work through like what the time is going to be, like how long is the ball in the air, and what the range would be if we're not given any information really about anything with numbers. And so how long the ball is in the air only depends on the height. Now, this is only true if its initial velocity is 0. How long it's in the air depends only on the height. That's if the initial velocity in the y direction is 0 meters per second. Okay, and so if you were to start talking about your variables in the y direction, I'm going to do it this way. I'm going to do initial position in the y and final position in the y, and initial velocity in the y direction and final velocity in the y direction, and then I'm going to put acceleration in the y direction and time. Time, remember, is our linking equation. And so if we talk about our initial position in the y direction and our final position, the final, when something hits the ground, the final position is going to be 0. And remember, for this, the initial velocity in the y direction is also 0. And the acceleration in the y direction is opposite g. And so how do we find the time? Well, we'll use my favorite kinematic equation that the change in position is the initial velocity multiplied by the time plus 1/2 acceleration times time squared. And notice how I automatically put this in my y coordinates, up and down height. So the change in y is just going to be, y final minus y initial. That gives us the opposite of the height, negative height. This term goes to 0. So I'm just left with 1/2 ay, the acceleration in the y, which is opposite g, or negative g, t squared. So when I solve for the time, my negatives will cancel, multiply by 2, divide by g. T squared is 2h over g, or the time is the square root of 2h over g. This equation holds true all of the time. If it's one-dimensional motion, if it's two-dimensional motion, it holds true all of the time as long as that initial velocity in the y direction is 0. So this is an important equation. I mean, you can always derive it, but super important. And so if we wanted to find the range then, like how far it landed, here, the range, the x information that we know the acceleration in the x direction is 0. That means the initial velocity in the x direction is the final velocity in the x direction, which I'm just going to call Vx because the initial is the final. And then we know that the position in the x direction, the initial position is 0, and x final is, let's just call it r for the range. And so the change in position divided by the time is the velocity, right? And so the change in position will be the range. And so we can find that range or the final position just by multiplying the velocity times time. So the range, which equals the final position, is going to be equal to the velocity in the x direction multiplied by the time. So you can then take the equation from the y over here, if you wanted to, and plug it into this equation here. You could say that the final position in the x direction, or the range, is the velocity in the x direction multiplied by the square root of 2h over g. If you're an equation memorizer, like, you can memorize this. I wouldn't memorize it because it's pretty quick to just derive it. So these two equations are basically all you need to solve this type 1 type problem where you're just shooting something off of a cliff.